In this video, we will be exploring some exponential base graphs. So first off, the base graph of an exponential function will always have the form y equals b to the power of x, where b is a number that is greater than 0, but not 1. Because if you had something like y equals 1 to the power of x, 1 to the power of anything is 1, so you'll just have a horizontal line. So we definitely don't want that because that would not be exponential. So we're going to start off by graphing y equals 2 to the power of x and then y equals a half to the power of x and see the differences, and then make some observations about properties. Now, since this is the first time we're graphing these base graphs, a table of values would be a good idea. So in my table of values, I've chosen some negative x's and some positive ones. And now I'm just going to do 2 to the power of each of those numbers. So I'm going to start with 2 to the power of negative 4. Now, if I wanted to be fancy, I can go into a fraction form because we can turn a negative number or a negative exponent into a positive one with a reciprocal. So this should be 1 over 2 to the power of 4, which is 1 over 16. But in terms of graphing, that's not the most useful for estimating the point. I mean, you can still use that. You're going to plot your point a 16th of the way from 0. But I'm just going to also write the decimal, 0.0625. And then for 2 to the power of negative 3, again, I can write 1 over 2 to the power of 3, which is an eighth, but I'm just going to go to the decimal. 2 to the power of negative 2 is 0.25. 2 to the power of negative 1 is 0.5. 2 to the power of 0, or anything to the power of 0, is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And 2 to the power of 4 is 16. Okay, so I'm going to go ahead and plot these points. So at negative 4, we're very close to 0. At negative 3, also very close. At negative 2, we're a quarter of the way. At negative 1, a half of the way. At 0, we're at 1. 1, 2, 2, 4, 3, 8, 4, 16. So we are growing at a pretty rapid rate on the right side. And here we are very close to that x-axis. Now, something to note, that x-axis, we're never going to dip below that. 2 to the power of x will never give us a negative number. If I do 2 to the power of a negative number, we'll still have a positive number, just very close to 0. 2 to the power of a positive number gets bigger and bigger, and again, positive. So this is actually called an asymptote. So this x-axis here, which is the line y equals 0, is an asymptote where your function is approaching it but never actually passing through it. Now let's go ahead and fill in this ratio column. So we've done first differences and second differences in the past where we take our consecutive y values and subtract them. But for ratios, we're going to be dividing. So I'm going to go bottom to top again, and I'm going to do 16 divided by 8, and I get 2. 8 divided by 4, and I get 2. 4 divided by 2 is 2. 2 divided by 1 is 2. 1 divided by a half is 2. A half divided by 0.25 is 2 again. And I can keep doing this, bottom divided by top, and I get a 2 each time. And you'll notice that the 2 matches the base in that parent function. And this is a common feature for exponential functions. They will not have a common first difference or second difference, but they will have a common ratio. Alright, so now that we know the shape of 2 to the power of x, let's see how it's going to be different for a half to the power of x. Now I'm going to start the same way with my table of values. Oh, and that's a little typo. It should be a half to the power of x. All right, so a half to the power of -4. I'm going to go the long way again for this first one. A negative exponent means take a reciprocal. So a half would become 2 and then to the power of +4. And that's 16. Now we've seen 16 before, but when x was +4 for the base function to 2 to the power of x. Now it just kind of flipped around. Okay, a half to the power of -3 is 8. And it's again because of that reciprocal, which turns the 1/2 to just 2 to the power of the positive number. A half to the power of -2 would be the same as 2 to the power of +2, which is 4. A half to the -1 is +2. Anything to the power of 0 is 1. A half to the power of 1 is a half, so 0.5. A half to the power of 2 would be 1 to the power of 2 is 1, 2 to the power of 2 is 4, which is 0.25. A half to the power of 3 would be an eighth, but that's 0.125. And a half to the power of 4 would be 1/16, which is 0.0625. So we have the same numbers here, except they're in the opposite direction. So what that means in terms of our graph, we're going to start high. At -4, we're at +16. Then we're at 8, 4, 2, 1, half, 0.25, and getting closer and closer to that x-axis. So this now is not growth anymore when I read it from left to right. This is a decreasing or a decay example. But something to take note. The y-intercept is in the same spot regardless of the change in the base, and that's because anything to the power of 0 is 1. So actually I'll make that note right now. The y-intercept is 0, 1, and that will be common for all base exponential functions. Now let me do the ratio. Bottom divided by top. So when I do 0.0625 divided by 0.125, I'm actually going to get 0.5. 0.125 divided by 0.25, half. 0.25 divided by 0.5, half. 0.5 divided by 1, half. 1 divided by 2, half. 2 divided by 4, half. 4 divided by 8, half. And 8 divided by 16, half. And once again, that common ratio matches the base of the exponential function. All right, let's go to some general properties that we can come up with. Well, the domain of both of the functions, one was increasing but going to the right and left forever. The other was decreasing, again going to the right and left forever. So our domain is infinite. Now, the graph is increasing. Which of the graphs was increasing? The first one, when the base was 2. So what we can generalize is, if the base is greater than 1, so if it's 2, 3, 4, then we're going to have an increasing function. And that's because that base is the number that is getting repeatedly multiplied. So if I'm multiplying by 2 or 3, I'm going to make the number bigger. But if I multiply by 0.5, a third, a quarter, I'm going to make my number smaller, which means when our base is less than 1 but greater than 0, we're going to have a decreasing function. Now, the horizontal asymptote. Both of these functions had a horizontal asymptote on the x-axis because the function was getting closer and closer to the x-axis, but we never actually went through or touched it. So the horizontal asymptote is always going to be y equals 0 for the parent or the base exponential function. The minute there's some sort of shift or some other transformation potentially, that asymptote will move. But specifically, if there's a vertical shift, then the asymptote will move. The range, we don't touch 0, so I'm going to put a round bracket, and then we go to infinity. When we calculated our ratios, it matched to the value of the base. So the common ratio is just that b value. And as a gets bigger, the graph is going to get steeper. And we're going to see that in the next set of graphs. we graph 2 to the power of x, and the next set we're going to graph 3 to the power of x, and we're going to see that the increase is going to be more drastic, and that's because our base is bigger. Because think about it, if you have 2 to the power of x, you're repeatedly multiplying by 2. If I had 3 to the power of x, I'd be repeatedly multiplying by 3, which is a bigger number, so the increase will be more drastic. So let's go ahead and actually graph 3 to the power of x and a third to the power of x. And once again, I'm going to do a table of values, but you really don't need to. Like, let me do the first one. For -4, I don't have to go to my table of values to know, oh, I should do 3 to the power of -4. I can look at my scale and say, okay, x is -4, so I'm going to go to my calculator. 3 to the power of -4 is, punch it in, 0.012, whatever. So close to 0. Then I would do 3 to the power of -3, and so on, and I can plot the points and kind of do a table of values in my head. But I am just going to do it properly this time around. So 3 to the power of -4 is a decimal that goes on forever. I'm just going to round it to 0.012. 3 to the power of -3, 0.037. 3 to the power of -2, 0.11. 3 to the power of -1, that's just a third, right, because of the reciprocal of the base. That's 0.33. Anything to the power of 0 is 1. There's that y-intercept. 3 to the power of 1 is 3. To the power of 2 is 9. Power of 3 is 27. To the power of 4 is 81. And if I do my ratio, when I do 81 divided by 27, I don't even have to actually calculate it. I know it should be the base, which it is. 27 divided by 9 is 3. 9 divided by 3 is 3. 3 divided by 1 is 3. And so on. The common ratio will be 3. Now, doing this ratio when I know my equation is kind of useless, but if I gave you a table of values and I didn't tell you what the equation is, a common ratio can help you determine if the function is exponential or not. Now let's go ahead and plot our points. So we have 3 to the power of -3 was 0.037, so again, very close to 0. 3 to the power of -2 was 0.11, then 0.33, so a third of the way. 3 to the power of 0 was 1, 3 to the power of 1 was 3, then we had 9, then we had 27, and then we were off the page. Now you can see I had to modify the scale as well to fit more, and this is a much more drastic increase as we're reading from left to right. Let's go to the next one. Now, just using my knowledge of the negative exponents and taking the reciprocal, when I do a third to the power of x, I am just going to start from these values and go up to fill in this column. So when I do a third to the power of -4, the negative exponent would turn positive by taking a reciprocal of the base, so that I have 3 to the power of 4, which is 81. And then 3 to the power of 3 would be 27 when I'm taking that reciprocal. So I can do that. I can use my knowledge of negative exponents, or I can go to my calculator to fill in the table. And if I were to do my ratio, now for the ones where I did estimate here, when I go to my calculator, maybe I won't get a third exactly. I might be off a little bit by a decimal or something like that. But when I do my common ratio, I should get approximately 0.33. Now, because I am using rounded y values, I get 0.324. So it's not the greatest, but it is close enough. So I'll actually write the real one. And then when I do 0.037 divided by 0.11, I get 0.336. 0.11 divided by 0.33. Okay, this one I actually get a third repeated. 0.33 divided by 1 is 0.33. 1 divided by 3, and so on. And it matches that base. So let's go ahead and graph that. So for -4, we were at 81, which is not on our page. At -3, we're at 27. At -2, we're at 9. Then 3, then 1, then a third, then closer and closer to the x-axis. But again, never actually touching it or passing through it. And once again, the y-intercept is 1 in both cases. So both functions have a y-intercept of 0, 1 and a horizontal asymptote at y equals 0. Vertical asymptotes exist as well, but not for exponential functions. The domain of both functions is -infinity to infinity, and the range is from 0 to infinity, but we're not touching 0 because there's an asymptote there, so I'm not using the square bracket. So which of the functions is increasing? Y equals 3 to the x, while a third to the x is decreasing. If I'm comparing steepness, 3 to the power of x is steeper than 2 to the power of x. And that's it for our base functions. So that base can change. It's not just going to be 2, 3, a third, a half. It could be anything. And anytime you want to create or draw your base function, create a table of values or do one in your head as you plot your points. But regardless of the base of that parent function, the y-intercept isn't changing, the asymptote, the horizontal asymptote isn't changing, and your domain and range isn't changing either.